Okay, so we talked about a frictionless ramp. I've still got it drawn up there. I just erased all of our little formulas on here. Neat thing about adding friction to it is most of this doesn't really change. Ultimately, what we have is just one additional force, which we already have a formula for. Yeah. All right, so let's talk about that. When we're talking about friction, main thing to think about is the direction that it will be pointing. All right, hiccups. I ate a chicken sandwich too fast. Stuck in my gullet. Anyway, so depending on which direction this thing is moving, your friction will change direction as well. If this thing is just allowed to slide down a ramp, well, then your friction will be pointing upward, all right? Parallel to the motion of the ramp. If the block is instead being pulled up the ramp by some additional force, well, then your friction will be pointing down. For the sake of this example, we're going to allow this thing to just slide down a ramp. There is some friction on the ramp though, so we'll have FF pointing in the opposite direction of motion. Your friction will always point in the opposite direction of motion. Okay? Now, this is again a simplified case. In some of the problems, there may be additional applied forces. Someone may be pushing harder down on this thing. Someone may be pulling it up with like a winch or something. Think about the direction of all your forces and what your net force has to be, all right? Your perpendicular components, the one downward from your weight and the one upward from your normal, as long as this thing is sitting on the surface of the ramp and only moving parallel to it, those forces will cancel out. Beyond that, it's just adding or subtracting based on what direction things are pointing, all right? So I would always recommend drawing a diagram, all right? If you've got applied forces especially, all right? Know what direction things are pointing, all right? These forces here, these two components of your weight and your normal force, those will always be there as long as you've got something sitting on the surface of the ramp on a planet, all right? The friction and any applied forces, the ultimate direction of motion, will change direction depending on the problem. But the two components of weight and the normal force will always be on it. All right, so if you're starting your diagram, that's always where I would start. All right, so now looking at our components and our normal force, finding friction and stuff, let's go through it. All right, your perpendicular component, well, that's still the side of a triangle. That triangle is still a similar triangle to the ramp that the block is on. All right, so we're looking for that side that is adjacent to our angle. We will be able to find the hypotenuse there by just doing mass times gravity to find our weight. So we're going to use a trig function that involves adjacent, the hypotenuse, and angle, which would be cosine. Okay? So if you want to find your perpendicular component, whether there's friction or not, it's going to be your weight times the cosine of your angle. Nothing has changed about that. Gravity does not care if there's friction. Gravity just does what gravity does. All right? So that will still be the same number. Your parallel component, again, it's a component of gravity. It doesn't care whether there's friction on the ramp. It's still finding a side of a triangle. In this case, our opposite side. So we've got our hypotenuse, we've got our opposite side. We can still use the weight times the sine of our angle, just like we did on a frictionless ramp. Nothing so far has changed. Our normal force, again, this block is not accelerating into the ramp. It's not flying off away from the ramp. So your forces that are perpendicular to the surface of the ramp itself must be the same. They must be equivalent, just in opposite directions. Okay? So our normal force will again be equal to our perpendicular force. Okay? So far, this is stuff we've already addressed. All right? The only thing that's really going to change on this is that friction exists on this ramp. It's not a frictionless surface. All right? And we already have a formula for friction. It was just your coefficient of friction, whatever the coefficient of friction is for whatever particular surface you have, times your normal force. We already have a way of finding our normal force. So if we're looking for friction, we can just do mu times Fn. Okay? Now, it may not always ask you to find the normal force first, so some people occasionally will substitute in what your normal force equals and write this equation as coefficient of friction times Fw cosine theta. Okay? So this is another formula for friction where you're just substituting in what your perpendicular component is for your normal force. The formula for perpendicular, right in there, because those two are equivalent, just in opposite directions. Okay? So we've got a formula for friction now. All right, now the size of that, the direction it's going will change depending on which way your object is moving, how rough your ramp is. All right, but we do have a formula for it that we can use. Okay? From there, think about our net force. Okay? Well, let's look at all the forces that are on this block, because last time we looked at all the forces and added them all together. Okay? So, forces that we've got on this block, we've got our perpendicular component, we've got our normal component, we've got our parallel component, we've got friction, and though it isn't applicable for this one, I am going to put it in here just so this is a more general formula for finding your net force for any ramp. All right, I'm also going to add any applied forces. All right, now the signs on these, all right, the direction of your friction, the direction of your applied force are dependent on what direction it's moving. Make one direction positive, one direction negative. All right, as long as you're consistent, ultimately your answer will end up giving you the same magnitude. All right. And again, our perpendicular and our normal are the same size force but in opposite directions. So when we're looking for our net force, these just go away. All right? So we're able to simplify it down a little bit. We end up getting our parallel force plus our friction force plus our applied force is equal to our net force. Now when you're actually using numbers, like from a problem, some of these will be negative. All right, your friction force will always be in the opposite direction of motion. All right, so if it's moving up the ramp, like it's being pulled up the ramp, well, that means that this is pulling up. These two would both be pointing down, which means your parallel component, your friction force, those have to have the same sign, either positive or negative, and your applied force would have to have the opposite side, or opposite sign. There we go. All right. So keep track of what's pointing down the ramp and what's pointing up the ramp. Those will change on a problem-to-problem basis, okay? So you need to be thinking about what direction they're going. Always draw a diagram for these problems. It really helps with figuring out what's going to be positive, what's going to be negative. You won't have as many hang-ups going along, all right? Now, for acceleration, we're not going to be able to simplify it as much as we did last time, unfortunately, because we've got these additional forces on there. When it was just under the effect of gravity, no friction, well, then we just ended up with only the parallel force, and dividing that by mass gives us g sine theta. It was nice and pretty. It's less pretty here, okay? You're going to have to deal with your friction, your applied force, but ultimately what you're going to be doing still is going to be your net force divided by your mass. Using Newton's second law again, it just doesn't simplify down as much. I guess you could simplify it a little bit if you didn't have any applied forces on there. Like if it was just friction and your parallel component, and we've got a formula for friction that could be represented with mass in there. Right? We could do coefficient of friction times mass times gravity times the cosine of our angle, and it could cancel out your mass when you divide it by it. But find your net force first, then divide by mass. Okay? It's not as pretty of a situation as with a frictionless ramp. So we don't need a perfect working equation for that one. All right, just figure out what your net force is first, and then divide by m, and then you're good. All right, main thing for this one is drawing your diagrams. All right, if it's being pulled down the ramp by some applied force, you'll have your parallel component down the ramp. You'll have your applied force down the ramp. Your friction force will be up the ramp. All right, your friction will always point the opposite direction of whatever direction something's moving. One more thing that is extremely useful: if you ever see a problem that says the block is moving at a constant speed, that is a huge amount of information, right? And it gets regularly missed. A constant speed means that your net force is 0, okay? If you ever have a constant speed in any problem, that means your net force is 0, which means that any forces pointing down the ramp will be equal to your forces going up the ramp. All right, that is a huge piece of information. Make sure you keep an eye out for it. It definitely pops up. All right. Beyond that, though, we're looking at vectors. We got component vectors. We're looking at the sum of vectors that are at 90 degrees and 180 degrees to these hiccups. 180 degrees to each other. Ultimately, what we're doing here isn't adding too much new stuff. It's just talking about a different scenario that involves things that we've already used. All right, if you've got a triangle, trig stuff. If you've got forces in exactly opposite directions, well, subtract them. All right, looking for your net force, make sure you keep track of directions. That's the main thing. Keep track of directions and look for anything that's going at a constant speed. Net force will be 0 in that case. All right, as you're going through the problems, make sure that you ask me for any help that you need and pay attention to the dimensions that it gives you for the ramp itself. All right, if it tells you the length of the ramp, that is talking about the hypotenuse of the ramp, not the adjacent side. Okay? There's also probably going to be some kinematics problems in there. All right, so when you run into those, think back to formula A, B, B prime, C, and D. Probably not 0. All right? I'm going to be uploading a video with data for a lab that we're going to be doing on Thursday. Other than that, we're working on ramps all week. Actually, the lab itself is on ramps, so we're working on ramps all week. All right, see you guys later. Remember, if you have any questions, ask Rob.